Hi everyone, and welcome to my talk about making games start fast. So, let's talk about history, just real quick. Let me tell you a story. Once upon a time, in the early 2000s, people started having bigger and bigger and bigger CPU, up until sometime around 2004, where, as you can see, they got into a small issue with the clock speeds. They could not continue the breathtaking pace of increasing the frequency. But luckily, after fiddling a bit with the problem, they figured out the solution. It was actually easy. You take one core, and since you can't make it bigger, well, you just make 4 smaller cores. And that's done. Easy. Problem solved. That was great. But then after that, I woke up. Hi, my name is Mathieu. I am a tech lead at Products Development Studio. I work on Hearts of Iron 4. Previously, I worked on Stellaris, and I knew Universalis and other games. And today, I'm going to tell you about Stellaris. In this talk, we are going to talk about threads. We're going to talk about logs. We're going to talk about how to avoid logs. And we're going to talk about threading efficiency and how to investigate it. So, in the interest of science and technology, I have decided to do this in a demo, in a live demo fashion, which is interesting because it bugged out like just less than 5 minutes ago, but it should be okay. So, you know what we're going to do? We're going to actually boot up the game. Let's see. I don't know if any of you have played Stellaris. You have like a minute to tell me about it because, as you will see, it's not super fast to start. I'm actually going to use a countdown on my phone at the same time. Do not count the launcher. I'm just going to check because, yeah, everything is fine. And I'm going to hit play. Now, you can see a marvelous splash screen that is showing you that the game is actually starting to do something. It's not the actual loading screen yet. The loading screen will happen in, I don't know, just about 20 seconds maybe. Fun fact, the loading screen was not part of the release. It was added later after we got the feedback that you click play on Steam and then you watch a blank screen for about 20 seconds until the game actually starts giving you any feedback. I really appreciate whoever brought that up. So as you can see, there you go. You should even be hearing the music. Just listen it for a second. You should be able to feel the space coming up. It's a space game. It's nice, right? Look at those great art pictures. You kind of want to see that space. You want to explore. You kind of want to go there. I mean, you might want to go there faster, but it's still pretty cool. And we should be in the main menu just about now. And my clock is saying 1 minute and 5 seconds. This is the main menu. Nothing special. I'm just going to exit now. That's nice. And I mean, most of our players actually have session times that are usually longer than 30 minutes. Like, people play our games a lot and for a long time. But still, we developers play it, start it a lot every day. So now I'm going to show you the secret beta that is not released yet. Don't worry, all the leaks are perfectly controlled. I am just going to check that everything is fine. Everything is fine. Let's hit play. This is the exact same game, except it's the unreleased version of the next patch. As you can see, it's a bit faster to start right now. If you remember the last time you heard the notes and the music, we're barely hearing the first notes of the theme, and we're already there. I have like something like 18 or 17 seconds. This is not a super strong machine, by the way. This is my home computer, and since I've been kind of lazy lately, I have not upgraded it. It is still a 2nd generation i7. It has like 4 cores and 8 threads, but I mean, it's not the fastest machine in the market. Still, I managed to go from like 1 minute to 20 seconds. So, you know, there's something. Yeah, that's kind of similar to the measures I had when I made this talk. The important thing is that there's the same amount of work that's being done in both cases here. Both versions are actually multi-threaded. It's not like I invented multi-threading in the 2.8 beta. It's already been there in the past. The difference is how the work is done. It's not really. Let's see. So I don't know if any of you have ever seen vTune, which is the tool I use mostly to benchmark and profile the startup. I'm gonna run you through it. This is a profile of the actual start you just saw a minute ago. As you can see, it takes about 60 seconds to start, and you have the timeline of your CPU and a bunch of threads. If you've never seen vTune, so the brown part here is the good part. It's the part you want to see. When everything is super brown like this, it means your core is just like going ham and just executing instruction after instructions. Doesn't mean it's the smartest instruction in the world. You can still have like very stupid code. You can still have a lot of issues with branch prediction, cache coherency, but at least your core is busy. It's spinning. It's doing stuff. Green is just meaning that the thread is sleeping. It has nothing to do. It's different from waiting from an actual variable. It's there, it's waiting, it has nothing to do, probably because the job system is not started yet. It's just there. It's there, it's created, it's just waiting for something to do. This light green, on the other hand, means it kind of wants to do something, but it's not doing much. It's basically sleeping on a condition variable, waiting on a mutex, something like that. It's basically waiting on a synchronization primitive in a passive way. Red is scary. It's historically a scary color in most cultures because it's related to the color of blood. And nobody wants to see blood anywhere, and especially not on his provider. What it means here is that there is a thread contention. When your CPU is just red, it's either spinning on a spin lock or just fighting. Usually it's fighting over something, fighting over a spin lock or something similar. It's not doing any actual work. It's just desperately trying to get some lock in an aggressive way. If we compare it to the new version that we will publish soon, you can already first see that the timeline stops at like 20-something seconds instead of 60, and there is much less red, and there is also a bit more brown in a bunch of places. Sure, you look at this, it's still not perfect for a machine with 8 cores. I mean, ideally, in a perfect world, we would have like just 8. You can't see my hand, but you would see like 8 big blocks of brown all the way. But I mean, it's still much better. So the question is, what are we doing? What is happening? Why do we take so long to startups? To give you an idea of what Stellaris is doing in this time frame, the first thing it is going to do is that it's going to enumerate all the asset files. I'll get back to that, but the big idea is that we do not know in advance which asset files we're going to load, because we have a pretty strong modding community and modding system. Plus, we have a bunch of optional expansion DLCs that you can or cannot have. And you can, even if you have them, you can disable them for some reasons. So we have to actually enumerate everything and see which actual assets we're going to have to load. The other thing we're going to have to do is that you're going to read the localization. Basically, every text string you see in the game, we're going to have to figure out which language you're setting up and read all the strings. It's basically a hash map. Globally, it's a hash map of a key and value. You just have to load everything from a bunch of text files. Then, of course, we're going to get to the more gamey parts. So we're going to load all the textures, we're going to load all the models, and we're going to load everything audio. So sound effect, music, all that stuff. And finally, we're going to load everything that is the game rules and the databases, which other people sometimes call scripting. It's a lot of things that defines how the game play out. And most of that is defined in script because first we want designers to be able to iterate faster. So that way it's not in code, it's in script. And also we want people, again, to be able to mod the game. And so we need to have that exposed to the user. So to give you an idea of the timeline, basically, we're gonna on the main thread, we're gonna start the enumeration in the background, and then we're gonna read the localization, and then we're gonna load the audio. You have the timings on top. CPU just means like the actual CPU time that the thread itself was burning, doing something, and the rest is just waiting on synchronization or sleeping. Once that is done, we're going to switch to another thread. This is just a technicality because on Windows, you have to have your main thread always reading the message loop, or the application looks unresponsive. So that's why it's happening on 2 threads, but it could be the same one. It doesn't really matter. We're going to load the 2D assets. We're going to load the 3D assets. And we're going to load the game databases. As you can see, there is a lot of waiting on the top. And at the bottom, not so much waiting, but a lot of CPU time. It's much better than the new one, but I think the best way of looking at it is an actual bar chart. So every bar on the left is the current release. Every bar on the right is the new beta that we're gonna publish in, I don't know exactly yet. The release date is not set yet. Blue means idle, so it's just you're waiting on something. And orange is you're actually doing work to some extent. Could be a spin lock, but you're doing something. Your CPU is just not sleeping. And as you can see, the difference is kind of tremendous and stuff like localization in audio, and still quite visible on 3D and 2D assets. And this is mainly why the game started in 20 seconds instead of a minute now. So let's try to break it down. What does that mean to have high CPU time? The most obvious option is your code is single-threaded, right? Like you could be using 8 cores, 10 cores, 20 cores. I don't know how many cores we make these days, but you're not. You have one thread, and everything in your computation is running on one thread. So obviously, like 7/8 of your CPU or how many cores you have is just not doing much. It could be better if it was a parallel algorithm. You could have an actual inefficient algorithm. Like maybe the way you process stuff is not good. Like, I don't know, maybe you have an n square or n cube algorithm where something could be done in linear or maybe n log n time. You could have, of course, more like technical CPU bound issues, like you have a lot of branch misprediction or a lot of cache misses, a lot of funky topic. Or you could just be busy on a spin lock. Since this is a talk about threading, I am gonna leave out inefficient algorithm and branch misprediction and all that funky stuff out of the topic. It's a fascinating topic, but it's not one that I want to address today, and it's not one that I needed to achieve those results. What about the wait time? The wait time could be due to disk I/O. We have to read stuff, right? There's a lot of textures, there's a lot of files to load. That's not free. You need to actually spin, or in case of an HDD, or just read in case of an SSD. You need to get that data from an actual physical drive. Could be network calls. For some reason, maybe you need some resources that are not on the machine, and you need to call a remote server to get them, and maybe you're stalling because you're waiting for the answer. Could be locks. Obviously, you can kind of guess that there is something due to that, like waiting on a mutex or semaphore or something else. It could be synchronization, which is kind of the same thing, but not really. It would be more like you're waiting on something to be done. Maybe you launched a bunch of computation and you have like a rendezvous point, and you hope that everything would be done by the time you're actually reading the value. For example, you're waiting on a future that is not complete, something like that. Funny enough, the only thing I did not have to touch to fix the loading problem was this IO. All right, so let's get into the actual issue, one of the main issues we had in our code, and that was locks. There's a great quote that I think I learned in another talk at ACCU. Sadly, the recording has been lost to bad equipment, but it's from David Butenhoff. I think he wrote that quote in on a mailing list, if I recall correctly. David Butenhoff, for those who don't know him, is the man who invented POSIX threads. I don't know if he invented them or implemented them, but he made POSIX threads, and he wrote a bunch of books about threads, and especially POSIX threads. And he wrote that great quote. He said, in the mail list, instead of picking up this stupid acronym, we should have called the basic synchronization object the bottleneck. So instead of mutex, like stud mutex, he would have preferred if it was not C++, but instead of stud mutex, what if we called it stud bottleneck? Maybe it would just make things more obvious for people. He continues on his email saying, sometimes bottlenecks are useful, sometimes they're indispensable, but they will never be good. At best, they're a necessary evil. And I think that explains mutex perfectly. To give you an idea, I continued on my profiling with Stellaris, and I'm gonna remove stuff that is not super important for that talk, especially because it's happening on secondary threads. But here is the idea of what my computation threads are doing during loading. Fizzfest, I'm going to come back to it in a minute, is a library we use to actually access the file system. And as you can see, for about less than 3 seconds time waiting on actual disk I/O, we spend almost a minute waiting on the mutex. As you may imagine, that's a lot. Basically, in this case, which it's a bit cheating because we're accessing hot cache, so half those files are actually not on the we don't even have to. We're not bound by SSD speeds. We are bound by like disk cache on the operating system. But even with a good SSD, even without the disk cache, just with a good SSD, you're still paying in some cases like 5, 10, 20 times the actual I/O cost in I/O to actually access the physical system. At this point, you would probably go faster if you would single thread it, because I mean, unless you have enough cores to compensate for the 20 times the I/O. And probably it won't even, because 20 times the cost probably would scale with the number of course fighting over a lock. So yeah, at this point, I think if I just changed all the code and said just load in one thread, I would have been faster. That's not what I did, but I could have done that. So brings us the question: why is there a mutex, right? Because sure, we're reading from the file system, but as far as I know, you can have two threads reading 2 different files, or 2 copies of the same file, for that matter, and that shouldn't be blocking every other I/O. So let's take a look at Fizzfest real quick. Fizzfest is an open source library that we use to handle the file system in our games. It's extremely useful for video games because it emulates the mounting features of Unix on every platforms, meaning you can mount folders, you can mount drives, you can mount archives, and everything looks like something that starts from a slash, and under it you can have as many subdirectories and mount points as you want. It's, as I said, per the author intention on his website, intended for video games. And I think if I have one criticism is that it's written in C, and I don't really like C, not anymore. I used to. So one of the good reason why we use this is because we need to have mount points in our video games. For example, if I want to resolve an asset in my game, I have to figure out where to find it in the game, because basically the idea is that we support overrides. So by default, you would have something like game/assets, which would be the main search point, but then we append more search mount points that should take precedence. The basic idea is that anything in the base game can probably be overridden by a DLC, a special downloadable expansion that would bring up, I don't know, maybe new models, better version of some assets, something like that. And of course, it can then again be overridden by modders because they want to actually modify the game. And of course, whatever they do should come first. The problem is the threading model of Fizzfest, because that library was designed in the early 2000s. Back in a time where I think most CPUs had only 1 core and or 1 thread. Hyper-threading would come up in 2003 or 4. So at the time, you could, unless you had like a very real machine with actual 2 physical CPUs, you would only have 1 process running at the same time. So people did not like do aggressive threading like we do in Stellaris. They would not try to start up like, I don't know, 6 or 8 threads just to access this, the file system in concurrency. You would just spend your time in the scheduler on the operating system commuting between the threads. There is nothing to gain there, and that's why when it started caring about threads, the biggest concern was thread safety. That's mostly what they were concerned about. Was that okay? If someone decides to be fancy and have like a second thread. We just don't want race conditions. So basically, what did they do? They put one big mutex on the API, and every time you get inside the API, you get one heavy mutex that blocks everything, which scale, as you might guess, very, very badly if you have multiple threads doing I/O. Excuse me, I have a lot of background sound. I think it's due to Slack. I'm going to see if I can kill it real quick. No, well, hopefully it will. If it comes back, I'll try to do something about it. Anyway, so what do you? What is the Fizzfest state? What is the mutex actually protecting? The first thing is mount points and library settings. The big thing is the configuration, right? If the user adds a new mount point while you're trying to seek a file, there's a risk that two variables will collide, and actually the file that is supposed to find is another one, or worse, they will start reading the same data structures and result in a race condition. There is also an open files list that is kept inside Fizzfest. I think it's mostly because the API being C, they do not handle ARII. And there is a mechanism, if you shut down the library, that ensures that if you have not closed some open files, it will close them for you. It's mostly a safety feature, but that means that every time you open a file, it has to put it somewhere in an open files list. You can also access the last error code, like error no on C, and it's per thread. And for some reason, it's also protected by a mutex. And finally, if you load archives like zips or other archive formats, you usually share the handle and then you make a copy afterwards. But there is a bunch of state that is kept for, I think it's caching, basically, performance reason. Like I think the index of the archive is only read once. So you have to be sure that only one thread is actually making the index of the archive, so that then the next one can just query it. So how did I improve it? Well, the first thing I did is that I changed everything to C++ because the C interface was making it a bit painful. I will not show code here, but there is a lot of macros involved to make sure that you release the mutex. I replaced everything with ARII logs. And then I started splitting the main mutex into several. Because, I mean, depending on which data structures you want, you don't care about the same things. So what I did first is that I initially removed the error code mutex, because turns out you don't need to lock something that is linked to the current thread. You can just use a thread local, and that solves the entire issue. I think the problem was, but there was no easy thread local at the time. And then the last part I did, I put a toggle. Because as it turns out, the main reason why we're always locking is that we always need to lock the mount list, the list of mount points. But when do you actually change that? Most of the time, you change it as the game is starting up. Sorry, there's really a lot of feedback with something in the background. I will try to remove it. I think it's due to Discord, and I will kill it right now. Oh, yeah. Please die, Discord. Thank you very much. Cool. Sorry about that. Yeah, so a big idea was you don't mount files and archives all the time. You mount them at the start when your game is starting up and you're figuring out which DLC and which mods are enabled. And once you're done with it, well, you're not going to touch it. So the idea was, if we can guarantee to the APIs, promise it, I swear I will not change the configuration from this point on, then there's no need for mutex, right? Because everybody can just access it. We could have done something similar with a read-write mutex, but I had some bad experience in the past with a read-write mutex. I just decided to go more simple and say, you know what? I'm just going to have a setting that says, I promise you, I am not doing any change to the configuration from this point on. I just put an answer to make sure someone will not break that promise later. And then every concurrent access would completely ignore the locking mechanic. So, well, the first thing we noticed after that is that the wait time on the Fizzfest mutex entirely disappears, which, I mean, yeah, we mostly bypassed it. So that's kind of expected. The wait time goes down because again, we are less waiting on the Mutex. The game starts a bit faster, but just not entirely faster, just a bit faster. And the CPU load increases, which I did not expect, right? Because like even if we remove the sleep time on the Mutex, we're not doing more work. We're just doing the same amount of work. So why is the CPU load increasing? That was weird. So I don't know if anyone has ever been in France, where I come from. We have these signs on most railroad crossings that says "Un train peut en cacher un autre." A train might hide another train. The big idea is that if a train is crossing, do not immediately go behind it once it's gone, because maybe there is another train behind that you cannot see because of the first one. And it's kind of the same idea. A lock may hide another lock. And guess what? There was another lock. Because we had our own wrapper around Fizzfest, just in case someone in the future would want to switch to another library. And I think on one platform we used to, but we dropped it historically. Anyway, someone had put a spin lock on it because, I don't know, 5-10 years ago, he got beaten by a bug on Linux. There was still a race condition in one case that the Fizzfest mutex was not properly protecting. It could be removed because that issue had been fixed. I had fixed all the race conditions by making sure that my very light locking was actually not hiding any issue. So I threw it away, and turns out, yeah, we got a bunch faster. The big thing was localization in audio, as you can see, lost the entire wait time. The CPU time for audio did not change immediately. I made another change, which I will come back later. But the wait time here and here completely disappears. And the reason why, if you remember, we said at the start that we were starting a background thread that would just analyze the file system and collect the list of the assets, enumerate everything. That was done in on 4 or 5 threads, and that was always colliding with the actual loading. So as we were trying to fetch the audio files, as we were trying to fetch the localization file, there was 4 or 5 other threads. We were trying to just scan the file system and list all the assets to be loaded in the next phases, and they would just collide with each other all the time, hence the wait time here. That completely vanished after the fix. So my early thoughts about locks after all that is that, as written in the quote, they make your code thread safe, but they will probably make it thread inefficient. Keeping a computation log-free will possibly require a refactoring to use another approach. In my case, I was lucky. Turns out that a read-write lock or another kind of or a promise that I will not need locking was able to do it. But in some cases, that doesn't work, and you might need to refactor your code. We're going to talk about it later on. And the last issue would be that sometimes you have an algorithm and you're like, oh, I might need to lock here because I'm not so sure about thread safety. And even if you want to be sure, you just add the lock, run it to a profiler, and it still looks okay. Potentially, it looks okay because you're already eating another bottleneck somewhere. And right now, your code is probably not run in a parallel fashion because another code is another reason is preventing that from happening. But maybe in the future someone will change that, and if he changes that, it will hit your bottleneck now. So what I'm saying is that you might, by adding a lock on something that is not highly parallel today, you might create problems for the future. I see there's a bunch of questions there. I will try to answer them real quick. Is vTune free? Yes, I'm pretty sure it's free. You just have to register on Intel's website and you get a license for a year or something. But it's free. I don't think I'm paying for it. Was the Fizzfest wrapper proprietary or a third-party wrapper? Yeah, it's the wrapper I'm talking about is really not a big wrapper. It's really just in our engine code. We have an engine Paradox VFS access, and we just either use VFS or use another API. It turns out that we've removed the alternatives over time, and Fizzfest is the only reason it's still there. So it's more like an interface, internal thing. It doesn't do anything special. It doesn't bring any improvements. But I think that might tie up with the third question. Were the C++ physical changes published? No. It's not because of copyright or anything. We're perfectly okay at Paradox with publishing them. The big issue is that in my quest to improve the code base and simplifying everything, I switched the build and a bunch of the code to C++. And I'm pretty certain that if there is a gaming library in C, the author will not switch the compiler just to get that fix. So basically, my patches themselves are not will not be able to work. What I did is that I made a blog post about it. That I have the reference at the end, which explains a bit more in detail with some code what I changed. If it's still not enough, feel free to come to me. I might try to actually contact the author, because again, my patches straight up cannot be applied because they just change everything to C++. Plus, I think we also flipped the standard mutex with like our own internal engine mutexes, which are just a wrapper, but whatever. So yeah, as is, they're not usable. And I will not answer the third question, the fourth and fifth question. This is just an old meme that doesn't want to die. Anyway, let's talk about Freddie now. Because, okay, let's say, okay, we want to improve stuff. Last question, I will take it afterwards to continue a bit with that section, just to be sure. All right. So we improve localization, we improve the audio, but 2D and 3D assets are still not loading super fast. As you can see, the problem is not so much the weight. I mean, there is some weight, and I think a bunch of that was reduced by the previous patch, but it's not a big deal. You see, by the end of 2D asset loading, there is not so much contention because the thread that was loading that was enumerating the assets is completely done. So there is no thread contention on the read part. It's just that it's just taking a lot of CPU time, I guess. Why is the question, right? So the problem is loading 2D and 3D assets was single threaded. We can probably guess that because if you look at there is not much contention on the logs, which kind of indicates that if there is no log finding on something that was accessing the file system, it's because there was no multi-threading. It's a huge speed-up potential if we can manage to actually spin more cores and load all that stuff in parallel. But we couldn't do that because Telarus was released in 2016. Development started a couple years before that. We're not a company that plays a lot with next-gen graphics, so we were still in DirectX 9s at the time. And DirectX 9 is not nice. Actually, it literally says in the description, Direct3D does not default to thread safe. When you're actually initializing it, you can ask for multi-threading support, but this will cause significant synchronization overhead. Basically, what it's telling us is, yes, we have a multi-threaded support. It basically means there's going to be a mutex on every of your call, and we're going to go back to the Fizzfest issue. So basically, the answer is like, just don't. Like, if you ask Direct3D 9, how do I do multi-threading? The answer is don't. I was at a dead end. I can't fix an API that I'm using. I'm not writing it. And a thing that I did not expect happened. Excuse me, my focus is failing. Okay. I got saved by consoles, which was very weird to me. I've been a PC player all my life. I owned a console for like a year back in '92 or something. I've never been into consoles. But guess what? When we made the Stellaris console edition, we work with a partner because we don't have a lot of expertise in consoles. And to put it on Xbox, it didn't have the choice because Xbox, I think it's 360, or maybe it's another one. I don't know anything about consoles. It does not support DX9 anymore. Instead, they had to switch to 11. So what we could do with the most actually of that work was done by my colleague and tech director, John. We just could take the renderer that they've made for Xbox and just put it back because it turns out they're very close to each other. Because I mean, the Xbox is kind of a PC in disguise. And switching to DX11 meant we could go back to trying to do multi-threading when loading assets. But of course, it meant that we had to rewrite the loading algorithm because it could not be an issue. Actually, for 3D assets, it wasn't hard. This is mostly a verbatim copy of the code that loaded the assets on Stellaris and that still loads them in the release version. We have I think it's a hash map of all the 3D types that are declared 3D asset types that are declared in the asset files. We just do a for loop for every entry, and for every entry we just say init for device, which basically is going to load up the models, the vertex buffers, the textures, blah 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 blah. How did we make that multi-threaded? We just put that in a parallel for, and literally the job was done. I could just go home and have a drink. That was a short day. Well, I mean, except I continued working on something else, but realistically, it was a very short day because the only thing I had to do was that, and it went from there to there. Because suddenly, instead of spinning one core, I was spinning like 8 or I think even or parallel 4 over commits, because it assumes that you're going to do some I/O, which in this case was actually a good idea because we do some I/O. We have at any time a bunch of threads are sleeping because they're waiting for I/O to happen, while the other one can just spin and just do stuff with textures and vertex buffers and stuff like that. So by spinning like 10 or 11 cores on an 8-core machine, we could just get about 1/8 of the time for the computation. That was great. And what it proves to me is that moving from serial to parallel doesn't have to be hard. Sometimes you're lucky. Sometimes your loop is already fulfilling any and all requirements needed to be replaced by a parallel algorithm, and you just replace your 4 by a parallel 4 and you can go home. The reasons, the things you need to guarantee in that case. First, your iteration should not write to any shared state, because if you write to a common shared state, you would need some kind of locking, and then you're back to square one. The order of iteration should not be important, because when you spin 8 or 10 cores into, on a big array and say you just get a chunk of it and just process it by yourself, you have no control of which will be done first. In most cases, it's not important, but in some cases it is. For example, in game logic, we have protections against that in some cases because we need the deterministic order. If you don't care about determinism, you can go with it. And yeah, again, finally, you should not have any locks, either because you're trying to protect a shared state, or, I mean, that's probably the only reason you want a lock. But if you have a lock, well, you're back to the Fizzfest issue that you're probably burning more time fighting over a lock than doing something actually useful. But what if you have to? Because I mean, it's well and nice, but I mean, it's kind of a cop-out to say, well, just don't do locking. Just don't have any shared state. Easy. Sometimes you do. Sometimes this is what you're having. Sometimes you have locks. Oh, no. Sometimes you have shared state and you need to lock. What can you do? You have 3 options. I mean, you have probably more, but that's the 3 easy one I could come up. The first one is make copies, because potentially the shared state you're writing to is actually not shared. It's just a working set that happens to be stored in the same place. And in that case, one of the solutions is just make copies. Make copies and make sure that everybody has its own working set. But sometimes those working sets actually need to end up together. And that's where you can use you can split the problem. I think it's called split apply combine or something like that. It's kind of like MapReduce and all those parallel classic algorithms. The idea is you make all your computation work on a private working set that you can run in a multi-threaded fashion. And once you're done, you combine all the results, and that is a serial loop. And the idea is that hopefully combining everything is quite cheap. It's basically aggregating some values. You can do it in one core, you're not losing too much. The last option you can do is try to be smarter about locking. It's kind of cheating, but sometimes it works. And I actually have a good example about that. Because let's look at the 2D asset load. It's, word for word with just a very small differences. It's kind of exactly the same code as the one we do. We take all the sprite types we have in our sprite database, and we just do a straight At first, I just said, well, I've seen that before. Just put a parallel for and be done with it. Sadly, it didn't work because if you get inside, that's what I tried first. Didn't work. Why? Because if you look at what our init for device stuff does, it does a bunch of stuff. But at some point, what it does is says, hey, call the texture handler and add the texture and just add the texture to that list. And then you're like, wait, graphics. That sounds like a sure variable. Texture handler, that sounds like something that may be shared. And in our case, it was shared. The texture handler is actually something in our engine that was in this generation of games was basically it's one big hash map. The goal is to reuse textures, right? Like if several different sprites share some textures, because some sprites are actually a combination of several textures with different effects. We do that a lot for buttons, for example, and a bunch of other stuff. We don't want to load the same texture twice. We want every sprite to refer to the same blob in memory. And so to do that, it's a hash map of a file name texture that is protected by a mutex. And that's a bottleneck, because every time I'm loading a texture, I'm basically waiting on the texture on the mutex. And that's, if I parallelize that, I'm just going to spend my time waiting here on this log all the time. So I started thinking, what can I do? The best option I had, my best idea, and I think the cleanest idea, would have to split in 3 phases. So the first thing would be, okay, has every sprite to declare which textures it needs, but do not bind them immediately, because that's the thing, right? Right now, we declare and we bind the textures in the same pass. The idea was to split that. First, you declare what you need, and that can be done in a parallel fashion. Then we take all the textures that have been said to be needed. We crunch everything into one list of unique entries, and again we spin that on whatever many cores you have, and we load all of those in parallel. Because again, every texture has its own entry. We guarantee it's unique. We can just load all of them at the same time. Finally, we pass back that stuff, and we go to all sprite and say, hey, this is the const shared texture handler. Just now you can update your pointers and have a direct reference to every texture. That would be my ideal option. The problem is, to do that, I had to refactor the entire sprite loading engine. And I didn't have like all week to finish that. So I tried something smarter, and I went for reducing the log scope. Because here's the idea. If you look back at this code, what it does is that it looks a mutex. Then it checks, is the texture already there? And if it's there, it returns it. If it's not, it just loads it and adds it. And actually, you can split that operation even at this stage and make the lock a bit more smarter. So here's what we did. We open the block, same as before. We lock, we check. Is the texture in the cache yet? If it is, great, we're done. We return and unlock the mutex. If not, we release the mutex and we load the texture. Then, once we're done, we take the lock again, we open the cache again, say, hey, do you have the texture this time? Nope, still not. Well, here it is. And if by some chance another thread managed to finish loading in the meantime and put it back, we just throw away the texture we loaded. It means that sometimes we're gonna have to double load the same texture and throw the copy away. But in practice, most of our texture do not share. It's a mechanism of sharing, but it's not so hard that we load everything 10 times. Most of the time, sometimes it happens that there is a double load, but in most cases it did not happen. I put like a counter somewhere just to make sure how many times we would dump a double load, and it's a very small thing. And how did and it actually worked. The time went down and the wait time did not go crazy. And the reason why I could get away with that was that the very slow operation that every thread is doing is loading a file from the file system. Actually, there's a missing brace here, or there's an extra brace here. I should fix the slide. And then this operation there, it loads the texture from the file system, and then it binds it inside inside DirectX by doing a bunch of text reconversion operation, feeding some stuff to the GPU. I'm not a graphics expert, but basically it's I/O, it's computation. It's gonna take some time. But it's why this heavy and costly operation is done. We're not locking. The only time we're locking is when we're trying to access a hash map and when we're trying to insert into an hash map. And that part is not really very expensive. And this is why I could tactically improve the locking without and get away with it. And yeah, basically that's what I just said. Tactical changes sometimes are enough to improve parallelization. I would probably get better games if I actually went for the first option I had. But I already reduced the time from 7 seconds to 1. Sure, I could probably get done to half a sec, but I would not gain 6 more seconds again. So it's a question of, it's a trade-off. With more time, I would. With just the time, it was a very good tactical one, and I was happy to take it. I see there's more questions. Let's see. Do I have or use any tool to verify data races were not inserted where removing locks? Yes and no. When I did it on Fizzfest, what I did is that I put an atomic variable to check if that told me if we were in promised read-only mode, yes or no. And then I put an assert in the API, meaning if at any point someone called the Fizzfest API to modify something, it would trap the assert. That was not perfect. I could have probably done more stuff with some stuff like what's the thing? Thread sanitizers or stuff like that. But I did not need to go all that way so far. Is there any other step in the future to speeding things up? For the startup of the game, I mean, I'm moving to another team now, so I don't know. There's probably still some venue for improvements, but to be honest, we already divided the startup time by, I don't know, like 6, 5. It improved us already. It improved the workflow of our people tremendously. I have some opinions about what I could do in the future, but that's maybe something we should take off because it's not related to those changes. Oriented identifier with an underscore followed by uppercase letter reserved in the standard. Yes, you should tell that to the people who wrote the code standard, my company. Anyway, wait, is that the right? Let's go quickly over the last bit that I have, which is trying to be asynchronous and smart in some cases, because we still have about 10 minutes to go through this. So, as you can see at the start, we have an interesting thing with 2 threads fighting over the same thing. One of them should be allowed to be read because the only thing it does is spinning on the input lock to give the illusion to Windows that the program is responding. It's a requirement you have to respond to. You have to pull the message queue every X millisecond or the thing seems to dead. And it's done in an aggressive loop. I don't think there is any sleep. We could improve that, but it's not really super important. The real problem was that it was still fighting with something else here. And I tried to take a look. The 5 seconds here were actually a busy wait on the network call. It was a busy wait on the network call. So what I did first is said, you know what? Maybe we don't need to busy wait on a network call. Maybe we can just put that in the future and get the result later. So I did that, and then I refactored to see where the data was used. It turns out it was not. It was a network call that was left from the past before we did some migration to the to use another launcher, and that network call was completely useless. The values read from it was completely useless. I did not need to wait 5 or 10 seconds for that network call to time out because I did not need the data at all. I just got 5 seconds back just by throwing everything away. I was pretty happy. But sometimes it's not that easy. Sometimes you have actually something that you need to do. It's just you need to be smarter about it. And the big question you have to ask yourself is, okay, you need to load all that data, but do you have to load it now? Because again, right, our goal is that we want to drop the player in the main menu as fast as possible so he gets the impression that the game is fast and reactive. But once he's in the main menu, he's not gonna immediately start the game. He's gonna start the game pretty fast, but in CPU time, he's gonna move his mouse, click on load game, select his save game, maybe click load, or maybe he's gonna actually start a new game. He's gonna do a bunch of stuff that feels like he's active, but by CPU terms, there's basically one core that is rendering a frame every 16 milliseconds or something and processing his inputs. And everything else is just nothing. The other 7 cores are probably asleep at that point. So what we can do is actually load a bunch of stuff at that moment, stuff that is not needed to load the data. And that's where the audio part comes in. Because here's the thing, I run a benchmark and it said, yep, your CPU time, your audio load is actually, it's actually a CPU efficient. It's not like you're sleeping on a thread. It's not like you're dumb or whatever. No, you're reading a lot of zip, because the main thing we have in Stellaris in the DLC folders is music packs. So basically, most of my time was spent on deflate. Can I optimize deflate further? I mean, maybe, I don't know. That algorithm is probably, inside Fizzfest is probably not super early. Maybe there is a more fancy, like multi SIMD version of it that could be better. I don't know. But also Fizzfest has a locker archive, remember, and we're reading from archives. So maybe even if we optimize unzip, it's not going to be that much better. So we can't even, like, multi-threading may not even solve the problem. But here's the question. How many music tracks do you need to display the loading screen in the main menu? You need one. At the end of the day, you need one. You need the main theme of the game, because that's what you hear. Da, da, da. That's the only thing you have. You don't care about the, I don't know, 40, 50 other music tracks we have. You'll need them once you start playing the game. But to display the main menu and to let people select their saves and show a loading bar, you don't need that. So until you're dropped in the game and you start interacting with the in-game music player, you don't care about all those other assets. And I know it's something that a lot of games do, right? They stream the assets. But in our cases, it's not something that is very baked a lot into our engine, because we're not level-based. Our games just, they load a simulation of the world and they play that simulation until you realize it's 3 a.m. in the morning and you have to go to bed. So there is, it's hard for us to predict what you will need when. So historically, the decision was made to just load everything else from the start. But for the music, we could probably do something smarter. So that's what I did. I just immediately started loading the main theme, because we need to play it. Until it's loaded and starts playing, we're not displaying the main, we don't want to display the loading screen. But everything else I could show in the background file with low priority and say, yeah, sure, whatever, do your thing. Once we're inside the game, I'm just going to rendezvous with that future and make sure everything is there. Again, potentially we could apply it to other assets, but in our case, it's complicated because we would have to be able to differentiate data and wherever needed. And sadly, there isn't much I could do immediately. It ties down to a big lesson, I think, which is if you know your workflow, if you know the user workflow, you can do a lot of things, right? Because if you know what data you will need when, you know the timeline and everything, then you can spread your loading all around and basically use the rest of the course when there is no urgency, like displaying menus and a bunch of other things that are actually not very CPU intensive. So we could do that for musics. We couldn't do that for textures. We could not easily do that for models either, because portraits can be, all the textures and sprites are used by the UI. And the in-game portraits and a lot of things. So we would have to segregate them in a way that we make sure that those are never used in the main menu. We would have to do the same thing for the 3D assets, which you can also see in the main menu, because the main menu actually, when you create your own empire, you have a preview of everything. So it could be done maybe with some smart lazy loading, but that would have been much more costly. It's a venue we could explore in the future, but right now we're like, no, just load everything in the simulation. And again, even with all that loaded up front, I still managed to get up to like, I don't know, 10 or 12 seconds, which is perfectly reasonable. So to wrap it up, and then I'll take the questions. Oh, I forgot to change that from another talk. You haven't seen anything. So locks will solve your thread safety problems, but they will cost you thread efficiency. And especially on modern machines with a lot of cores or threads, you will feel it if you start to go if you try to thread your algorithm. If you need to lock to parallelize, consider another approach. Consider refactoring. Consider possibly locking in a smarter way if possible. That's not always possible. And finally, do not overestimate the potential gain of revisiting all the code with threading in mind. I think that's the biggest thing, right? When I started this this whole campaign of trying to make the game start faster, my initial idea was completely different. I thought the problem was because I had observed that on another game. The Windows file system is super slow to load a lot of small files. And that's a problem on the Open Universalis, for example. I assume it would be the same issue, and I was trying to do something smart like Git does, and that was my whole venue. It turns out I never needed to even remotely touch that because that was not the problem. The problem was locking. The problem was I could thread smarter. And I mean, I've been in this profession for what, 15 years now since I got out of school. I don't consider myself a newbie. I go to a lot of conferences. I know that stuff, but never would it have crossed my mind that I could just take my existing operation that takes a minute and put it down to like 12 or 15 seconds. I thought if I got like half, that would be miraculous. So yeah, never underestimate the potential gain of reviewing over code and trying to work with threads. Machines have really changed from, especially in my case, from when I was in school and from the previous applications I worked through. And there's a lot of gain because even if you thought about it, maybe when the previous guy did it, it was not worth it. It's there's a whole venue there. Oh, and furthermore, I think your build should be destroyed. Thank you. I'll look at the questions that are remaining. Do I have any insight to what DirectX did to improve concurrency support? I am not well versed into graphics, but I would assume that somehow with modern graphics pipeline, you can actually queue up operation of loading textures, copying texture, whatever, in a way that does not require locking concurrent variables. I mean, if some people from NVIDIA or whatever are around, maybe ask them, because I am really not an expert on it. I don't know if Bryce is around. If he is, probably ask him. I don't have a great answer for that, sadly. Do you know if your improvements had significant impact on machine with less cores? I haven't tried with less than 4 cores, and like that would translate to 8 threads. I gave the patch out to our testers and our beta testers. I think our game requires at least 2 threads to start because we have a busy loop, as you can see, because there's a busy loop pumping the messages and another one. We actually had a bug. Someone tried to start our game with a single core and he got stuck in the loading screen. I think we have a requirement that you need at least 2 cores to be able to start up the game. It's not ideal. We could probably improve it. But I would assume that even if you have only like 4 logical threads, you would see something. And if you have more, you can probably see more. I know, for example, that these improvements have been put back in the modern engine, and CK3, Squeezy Locking 3, our latest release, benefits from them from the start. And I think one of my colleagues just bought like a crazy Threadripper or like something just below the Threadripper, and he noticed some insane improvements. Like CK3 started almost twice as fast after I merged those change back into the trunk version of the engine. So I think it scales, and I think you still get something if it's a bit smaller. Question number 10. Do you think game developers would benefit from a deeper understanding of parallel patterns? I cannot speak for others. I have no idea. I think everybody should benefit better from like knowing about threading and everything like that. Because I studied all that stuff in school. I guess I did not apply it a lot for a long time. My previous job was a finance application that did not use thread because a lot of their models were dating back from the pre-multi-threading era. I knew all the theory and I could apply it when I did it. It's just, I don't know. I think today, if you want to do something fast and reactive, again, if you care about latency, like how fast the computation will go, yes, it's obvious that you probably need some kind of background on threading and how to improve that stuff. Has this caused you to move to a different file system in the future? I mean, I can't change the file system itself, right? Like I'm still stuck with NTFS. I've been toying with the idea of trying to have an archive file instead of putting the files. We're running out of time. I'm just answering that question, and for the rest, I will have to take them offline. I have considered replacing the game files that are on the file system by zips, but the problem is it breaks the workflow of the modders and all developers that are used to work with flat files and don't have to rezip everything every time they want to publish or make a change. We could improve that by having like two modes. Like one of them is basically the release version that packs everything, and another option for the development thing. But that will require longer term changes. I am not opposed to it, but again, it's time, right? Like I have everything. There's a lot of things I could improve in a lot of places, and I'm pretty sure you guys have the exact same thing, feeling about whatever you're working on. There's a lot of time you can improve stuff. The question is, how much time and effort can you put into it? And yeah, I answered the question. Yes, the new, I mean, yes and no. The new engine already has some of those improvements, but for the rest, I don't have. The question was, will you develop a new engine for future projects to incorporate these ideas from the start? We will. We continue. We have an engine that we continue improving over time. Some of those things have been improved. Some of those learnings have already been applied, but I did not have them in Stellaris. For the rest, I guess it's up to my engine team. I think yes, but again, time. And I will have to stop here, but I will probably hang out in the room and take over questions. I have like 10 minutes before the lightning talks happen, maybe 15. So I'll be in some table on the first floor. Thank you, guys.